So welcome to this next lecture. Having gone through the very simple room heating and relative humidity regulation control example, it will be appropriate to look at the major steps that are involved in designing a process control system. So the control problem must be properly formulated. That's always a well formulated problem is a problem that's half solved. And the formulation of the control problem first and foremost requires concretizing an abstract idea into quantifiable metrics. For example, in our room example, human comfort of the occupant is translated into quantifiable metrics of temperature and relative humidity being acceptable in a certain range. So user comfort is equivalent to right temperature and right humidity, and temperature and humidity are things that can be measured. These are quantifiable numbers. Then what we need is we need to clearly articulate what is the desired state of these quantifiable metrics, temperature and humidity, output process variables. So this determines this articulation of the desired state. What is desirable? How would I like my system to behave? This articulation fixes what process variables to control, at what value to control them, and how tightly to control them, what is the acceptable deviation of these process variables around their set points. In order to properly formulate a control problem, you need to know exactly how many control degrees of freedom are available for you. While the room example was quite trivial, for complicated process flow sheets, just accounting for control degrees of freedom can get confusing. It gets complicated for chemical processes. Note that one control degree of freedom can control only one process variable. Now, because you are limited in the number of process variables that can be controlled, because you are limited in the number of manipulated variables that are there, the same control degree of freedom may be used for controlling a process variable in one operating regime and another process variable in another operating regime. Case in point is single control degree of freedom in the room example, which is the heater duty. So normally the heater duty would control the room temperature, but if the relative humidity goes too low, the air becomes too dry, so much so that it can cause nosebleeds, then you adjust the heater duty to hold the relative humidity at the minimum acceptable level, and then temperature floats. So normally heater duty controls temperature and relative humidity floats. On a particularly cold, chilly, dry winter day, if the relative humidity goes too low, you use the heater duty to hold the relative humidity at that minimum value, and then the temperature floats. And usually the temperature would be lower than desirable. Let us say the desirable value is 25 degrees Celsius. Perhaps the temperature floats around 15 then, because you are not heating as much, because too much heating will cause the air to be drier, and you don't want the air to be too dry, that is too low a relative humidity. So the controlled process variable may shift from one to another process variable depending on where you are operating, depending on the operating conditions. And this shifting of process variables from one to the other, this requires a clear understanding or a clear prioritization of your control objectives. What is more important and what is less important, and what is more important gets controlled by the available control degrees of freedom. what is less important floats, operating condition changes, the prioritization changes, and therefore the set of process variables that are controlled changes. And this prioritization is necessary because typically when you're trying to enforce a certain dynamic behavior on a process, that means you want process variables to be within bounds, not exceed maximum or minimum limits, and so on and so forth. In other words, you are trying to ensure that all process variables satisfy certain constraints. The process variables satisfy certain constraints due to safety, stability, customer care, quality, those kinds, economic considerations. Most often the number of constraints are much more than the number of manipulated variables. Ideally, I would like to control all the constraints all the time, but since the number of manipulations that you can make is limited, therefore you have to prioritize what is more important, what is less important, and then use your control degrees of freedom to control what is more important. So this prioritization of the control objectives actually fixes what process variables get controlled and what other process variables float. Once a control system problem is properly formulated, then the next step is to solve the control problem, and there are some fundamental principles that cannot be violated, that are always true when solving the control problem. First and foremost, you control a process variable using an MV, a manipulated variable, or a control degree of freedom with a strong and predictable response. What do I mean by strong? Strong means you make a change in the process variable, you make a change in the control input in the MV. The process variable responds quickly, that means a fast dynamic response, and the magnitude of change in the process variable is large. So let's say you got two process variables and you look at their responses. One response is this, another response is this. So this is slow and small, this is fast and large in terms of magnitude. This is what I would call strong, slow and small. This is what I would call weak. So only if you have a strong relationship between a PV and an MV should you control the PV using that MV. What do I mean by predictability? What do we mean by predictability? See, predictability is something that means, I mean, the linear system thinking that we all have. So if I change input by delta U, output changes by delta Y. If I change input by 2 times delta U, output changes by 2 times delta Y. This is the linearity assumption. If I change input by delta U1, output changes by delta Y1. If I change input by delta U2, output changes by delta Y2. If I change the input by delta U1 plus delta U2, output changes by delta Y1 plus delta Y2. This is the classic superposition principle, linear systems kind of response that one expects. In chemical processes, however, the dynamic response changes depending on where you're operating, depending on your operating condition. Okay, so much so that for highly nonlinear systems, you could have, for example, if I change input like this, output responds like this, let us say. At a different operating condition, same change in input, output responds like this. Now it's gone. You see, this change is positive, this change is negative. So this is like saying, okay, if I increase the steam, depending on where I am operating, the temperature increases. But if I am operating very far away from the nominal steady state, the temperature may also decrease. So because of recycle, chemical processing systems are more nonlinear, and nonlinearity implies, this sort of superposition predictability does not hold. Now, as long as the nonlinearity is not too severe and you're sort of guaranteed, okay, if I increase steam, temperature increases, guaranteed. The increase may be per unit increase in MV, the increase may be in the temperature, per unit increase in the steam. The increase in temperature varies between 1.5 to 2.5%. So there is some uncertainty there, there is some unpredictability there, but the directionality is fixed. So there is a noticeable response. The response may be more or less, but nevertheless it's guaranteed to be there. Yeah. Depending on the operating condition, the response also may become faster or slower. So if you're operating, let us say, somewhere, response is like this. You operate somewhere else for the same change in the input, response is, let us say, faster and larger. Well, faster would usually be smaller, so faster and smaller, maybe this is what you expect to see in practice. Yeah, that's more usual. So the point is, the dynamics of the system change with where you're operating. Now if this change or uncertainty or unpredictability in the dynamic response is not too severe, then controlling that PV with that MV makes sense. But if it is very severe, to the extent that if I increase steam, depending on where I'm operating, increasing the steam can cause the temperature to increase, or it may also cause the temperature to decrease, that's unpredictable. So you can't do control then, because you don't know what to do. Should I increase the steam or should I decrease the steam? Don't know. It depends on where you are. So solving the control problem requires that the PV-MV response be strong, that means fast and large, and it be predictable. The nonlinearity be not very severe. Okay, so that's what I mean by strong and predictable, and this is usually ensured by close-by pairing. What do I mean by close-by pairing? Hang on. What do I mean by close-by pairing? So let's say you've got 3 tanks in series, and we'll just look at controlling the level of the third tank. Now I can control the level of the third tank this way. I may also control the level of the tank this way, and what that means is, this way, and this is under level control and this is under level control. But you see, this loop is a long loop. So I make a change in the fresh feed, that change must pass through tank number 1, then it must pass through tank number 2, and then the change in the flow to the last tank, the third tank, change. So level will take a long time to respond to changes in the feed flow. So this long level loop will make control of level in the third tank difficult, whereas if I do this guy, close by pairing, the level will be controlled robustly. So this will be fragile level control, this would be robust. So this is what I mean by close by pairing. When you pair the process variable with a manipulated variable that is close by, strongness and predictability is more likely, and because the response is strong and predictable, control is going to be more likely robust. Okay. Now, when we want to control, the simplest way for controlling a process variable is to apply feedback. Just see where the process variable is, compare it with what is the desired value of that process variable, and then make an adjustment to the manipulated variable using a proportional integral or proportional integral derivative, or perhaps even on-off if cycling is okay, kind of control algorithm. So feedback is the most robust way of trying to drive a process variable to its desired value, to its set point. So use output process variable feedback for control, because this is the best way of doing it, the most reliable way of doing it, the most robust way of doing it. Prefer the simplest control system that achieves the objectives. So for example, in the room example, I would say on-off control is just fine. You don't need a P controller or a PI controller or a PID controller, because all that you're interested in is that the room temperature should be let's say between 25 plus minus 2 degrees Celsius. And if you remember the response that we saw for on-off control in the previous lecture, the cycling in the temperature, this band was I think 3 degrees Celsius, something like that. So obviously if I choose my set point right, one can make the room temperature to cycle between 27 and 23 degrees Celsius, which is 25 plus minus 2 degrees Celsius, and this is perfectly fine. There is no need to complicate it further by using a P controller or a PI controller or a PID controller. Okay, so one should prefer the simplest control system that achieves the objectives. My objective is having the temperature in a range that the user finds comfortable. So I really don't want very tight control of the temperature. 23 to 27 degrees Celsius is fine. Simple on-off control gives that. So just put a thermostat and run it. If you want to do PI or PID control, there are two problems. First of all, you need a temperature sensor. Thermostat is a temperature sensor in itself. If the temperature increases, the thermostat starts bending. As it starts bending, connection gets broken. As connection gets broken, the heater switches off. Then things start cooling off. You know what a thermostat is, right? It's two different metal sheets with different conductivities that are joined together. And then as temperature increases, because the thermal coefficient of expansion is different, the metal tends to bend. And let us say the bending is in this direction as temperature increases. So as temperature increases, when the temperature is low, connection is made. But when the temperature increases, this guy bends and the connection gets broken. So low temperature, the state is like this. High temperature, the state is my drawing is not so good, but I hope you get the idea. Let's see. Okay, so connection is broken. High. Yeah, so circuit is complete here. So current flows. In this case, current cannot flow because the circuit is broken. So if the temperature is high, the heater stops. Heater is switched off because current flow to the heater stops. If the temperature is low, circuit gets made. Circuit is complete. Current flows, and therefore the heater heats. Yeah, it's a very simple system. Doesn't require a thermocouple or an RTD sensor or a specific temperature sensor. More than that, it also implies that all you need is just two states for the manipulation, on or off. Whereas if you want to do P, PI or PID control, what you want is that the heater duty value between 0 and 100%, all intermediate values be accessible. So you need a more sophisticated manipulation mechanism. So obviously with P, PI or PID control, you need a temperature sensor, you need a more sophisticated manipulation mechanism. So the system is more complicated. Sensor may fail. Also PID control algorithm, you got Kc, tau I and tau D, three tuning parameters whose proper values must be chosen. If you choose inappropriate values, you can have a closed loop response, a controlled response that is either too sluggish or too aggressive, that causes cycling, that causes the temperature controller response to be like this. This is the same as on-off control. Yeah, so depending on the degree of tightness of control that is desired, you choose the control algorithm. And the simpler the control algorithm, the simplest control algorithm that achieves the objective, that's the one that should be used. Because simple is robust, complex is fragile. And one example that you may find, simple people are generally happy people. Those who think too much, those are the ones who sooner or later end up getting depressed because they were too smart for their own good, So prefer simplicity over complexity. On-off control results in cycling, and you typically do not want this kind of cycling in chemical process systems because you're dealing with hazardous chemicals, so you want the temperature to be where it is. You really don't want things to cycle around because of control. So in chemical process systems, P, PI and PID controllers are very commonly used, PI being the most common. Yeah, and one of the simplest ways of doing control is to have multiple single input, single output controllers. And then we can have some enhancements such as, where necessary, apply feed forward or apply model based control coupled with feedback. Yeah. So the norm or the industrial norm is multiple single input, single output controllers with appropriate enhancements wherever required. That's the norm that you would see across all kinds of systems: mechanical, aerospace, chemical, electrical. Control using process variable feedback is simple and effective. It's simple and effective because it is direct. You're not relying on some kind of a model. You're relying on direct information. I want the process variable to be here. Right now it is here. I want the room temperature to be 25 degrees Celsius. Right now it is 20 degrees Celsius. So increase the heater duty by so much. Yeah. Very direct. No beating around the bush. We've also seen that economics plays a major role in determining what to control, what process variable to control. And good economics typically translates to proper choice of what is controlled, proper choice of the process variables that are controlled, that is the choice of the CVs and their set points, the value at which they are controlled. Many a times the set points are constrained to be either at a maximum or at a minimum, active constraints. Sometimes the set point is unconstrained. Unconstrained meaning set point can vary from here to here, but optimum value is somewhere in between. And the optimum value can shift due to disturbances, so it may go from here to here or here to here. So then you say, okay, how do I do this adjustment? To do this adjustment, we look for that process variable whose optimum value remains nearly invariant with respect to disturbances, and then by controlling that particular process variable whose optimum value remains invariant due to disturbances, you ensure near optimum operation all the time regardless of disturbances. So good economics actually determines what to control. Now when you're doing control, you know what to control and you got the available control degrees of freedom. So let us say there are n manipulated variables and I have decided that using these n manipulated variables I'm going to control these n output variables, CVs. There are all kinds of disturbances, there are all kinds of other process variables that are measured. Now there are two extremes to control. Centralized control, where you have a single controller that takes in the set points of all the process variables that you're controlling. It takes in the values of all the controlled variables, any other measurements including disturbances, including what is the value of the valve positions. These are also, this is also a process variable, this is also a process variable, this is also a process variable. All these values go into the multivariable controller, and depending on the values of all the CVs and the available PVs, there is an algorithm that accounts for the effect of this on that, that on this, the disturbance on the process variable, etc., etc. It tries to account for all the interactions, and based on those interactions it decides how each of these valves should be moved. That's centralized control. What is the problem with centralized control? Complicated. If it is complicated and let us say one of the sensors fails or one of the pieces of code misbehaves, figuring out what is going wrong becomes very difficult because everything is coupled to everything else. Yeah. So these kind of complicated control systems usually end up being very fragile. What's the other option? Other option is we'll just use CISO controllers. So this is what I show here. So we control CVN by manipulating appropriate manipulated variable, CV2 by manipulating appropriate manipulated variable. You know, all of these are CISO controllers. This is a CISO controller, so is this, and so is this. What is a CISO controller? Changes are made to the manipulated variable based only on changes in its controlled variable. So this changes based only on this. This changes based only on this. And this changes based only on this. Yeah. So in a sense, each of the controllers is blind to what the other guy is doing, even though what this guy does disturbs that guy and what that guy does disturbs this guy. So this is the simplest control system and it's called decentralized control. Decentralized meaning, why is it called decentralized? It's called decentralized because everybody is doing their own thing. They are free to do their own thing and not worry about what the other guy is doing. That's a decentralized system. Okay, so this is the simplest possible control system. Typically what is done is you have the simplest possible decentralized control system and then you implement enhancements to it where necessary to improve the dynamic control. What kinds of enhancements? There are all kinds: feed forward, model based, ratio control, which is a kind of feed forward control, cascade control, optimizing control, and so on and so forth. We will talk about these enhancements in this course. So what is implemented in practice is enhanced decentralized control. What you have is decentralized control systems with multiple CISO controllers and local enhancements, feed forward, model based, etc., to improve dynamic control where necessary. Almost all industrial control systems are of the enhanced decentralized kind. So now in designing an enhanced decentralized control system, what are the steps? First step is always formulating the problem, and formulation of the problem is having control objectives with their prioritization, because this determines what process variables to control, how tightly to control them, and which is more important, which is less important. The prioritization. Once you know what to control, next step is to design the enhanced decentralized control system. Control structure design, basically, if there are n process variables to control using n MVs, which process variable gets controlled by manipulating which manipulated variable? This is a combinatorial problem. If there are two variables to be controlled using two manipulated variables, there are two pairings that are possible. You know, one process variable, manipulated variable. There are two process variables, there are two manipulated variables. You may do 1 1 1 2, or you may do 1 2 1 1. So there are two possible pairings. If you have three process variables, you will see that there are 6 possible pairings. You know, it goes as n factorial, I think. Yeah, so there are n factorial possible. So you see the number of pairings blows up exponentially. But then if you apply this idea of the pairing, using that pairing which ensures a strong response as well as a predictable response, which essentially means control a process variable using the nearest available control degree of freedom, because that is what ensures a strong response that is fast and large in magnitude, as well as predictability in the sense that the response is always in the same direction, dynamically similar. Yeah. So if you apply this, then this n factorial actually reduces down to some very few options, very few reasonable options, by applying the close by pairing philosophy. Once these CVMV pairings are decided, then you figure out targeted enhancements to the decentralized control structure to improve control, and these targeted enhancements, cascade, feed forward, model based, are usually obvious to an experienced control engineer in the first pass. So he'll do it in the first pass anyway. And once the control system with the enhancements are there, the last step is to decide on the control algorithm and the tuning parameters. For example, if it's a PID, first of all you got to decide whether I should use a P controller or a PI controller or a PID controller. If you're using a P controller, then what should the gain be? That's the tuning. If you're using a PID controller, what should Kc, tau I and tau D be? Yeah, that's the next step. And in order to do all of this, I hope you realize that process understanding is key. What process variables to control comes from process understanding. What is the degree of tightness that you desire? That also comes from understanding what the process is supposed to do, the context in which it is supposed to operate, the control objectives, etc. So process understanding, I cannot overemphasize, this is always key. If you understand your process well, you will be able to control it properly. And usually most control problems are due to poor process understanding or flawed process understanding. With this, we come to the end of this lecture. I hope you enjoyed it. See you next time.